Hello, welcome to this second lecture on detectors. In this lecture, we are going to basically look at the mathematical representation of signal and noise. We will invoke some basic mathematical relationships, first the basic mathematical formulation. After that, a few basic relationships like the Fourier transform and going back and forth between the time and the Fourier space and so on. So let us begin. So consider a signal, and the signal is always going to be real for us. So V underscore ST is basically the voltage due to the signal in my detector. Uh, the signal is centered at omega. Omega is like the carrier frequency, if you like. And the amplitude Vs is actually a function of time. And that is where the basic content of the signal is coming from. So at my detector, I not only have the signal Vs of t, I also have instantaneous noise. And the noise is of two kinds. Because everything is real for me, there is a noise that is in phase with the signal. I call that as in phase noise. And there is also a noise which is out of phase with the signal, which is at 90 degrees out of phase, which is called the quadrature noise. Now you see, noise is of different kinds. The noise and these two particular considerations, that is one, the in-phase noise and the quadrature noise, kind of captures all the possibilities that one might construct of the incoming noise. Clearly, the noise again is centered at my carrier frequency, which is omega. So you see you have here, so for example, you have here Vn of t, right? This has got the first term here is the one which is the in-phase noise. The second term here is the quadrature noise. You can see that in phase, because cosine omega t dependence is precisely the dependence that we have in the signal, hence this is the in phase noise. And its amplitude is given by VNC. Here C stands for the cosine, whereas VNS, where S stands for the sine omega t or the quadrature noise. Clearly, the amplitudes of these are going to be time dependent and sort of random. And similarly for the in phase and the in quadrature, I mean both the aspects of noise. And there are a few other considerations that I want to talk about. That is, if you look at these amplitudes, these are slowly varying functions of time. They are of course random, they are uncorrelated, they are quantities which are sort of independent. They are both independent of each other. And the interesting part is, because this is noise, these voltages will actually average to zero, right? So again, we will talk about what do you mean by averaging itself, but this is the basic formulation of our system, or for of our input to the detector. So the total field at the detector is simply, the signal, right, which had a cosine omega t term and the noise term. That is precisely my total signal, which is at the detector. Now, what we are going to do to consider this in a more meaningful and mathematically elegant way is to invoke something called the complex notation. So even though my signal itself and my noise, everything that I detect on the detector is real, I introduce this complex notation only as a mathematical ease. One one can do the whole analysis considering only everything being real, but then there is a certain ease with which one can accomplish you know, um, multiple tasks and multiple ways of looking at the signal and noise using the complex notation. You will see the benefit of it as we go along. So all that one is saying is that my V signal, right, which is this quantity, uh, the V signal here is such that uh, it has again got the central frequency, and Vs of t is exactly the same coefficient that we had considered earlier, real coefficient, but this has got this exponential I omega t, and clearly the signal is simply the real part of this expression, right? Similarly, if I'm looking at the in phase and the in quadrature parts, again, let me re-emphasize that Vs of t, the capital Vns of t, and the capital Vnc of t, all three of these quantities are actually such that they are the same as we considered for the real signal, right? It is simply that if I want to look at these amplitudes per se, I should simply consider the real parts uh, of these expressions, and I would get to the real amplitude. So anyway, so let's look at now the total field. Clearly, the total field here is V of t, which is at the detector. This is same as what I written on the top, and it is simply the real part of these complex quantities added together. Now remember, Vs of t times exponential I omega t, its real part is the cosine. Similarly, Vnc is the in phase component of the noise, and which again is cosine omega t. Whereas if you look at the in quadrature part, remember this was supposed to be Vns sine omega t, and you will clearly see how we have gone about it, because you see that Vns exponential I omega t, its uh, real part is going to be cosine, and its imaginary part is I times, right, I times sine omega t. So I'm multiplying by minus I to make sure that this gives me the sine omega t that we talked about in my previous slide, right? So this is what my notation is going to be, that my V of t is simply the real part of the addition of all these time dependent amplitudes, of course appropriately added. Particularly note this minus I sign here to ensure that we get a sine omega t as the in quadrature component. So VNST will become the in quadrature component whose phase is basically the arising out of the sine omega t part of the function, right? So my total signal V of t at the detector is simply the real part of this V of t. Let us look at this a little pictorially. So this is what you're familiar with, also called the phasor diagram. So what I'm plotting is basically the real part and the imaginary part of my signal at the detector, right, which is just capital V of t exponential I omega t and its real or imaginary parts. Then you see that my Vs of t is some sort of an amplitude, right, uh, which is of course time dependent. To that, in phase, that is, there is no phase difference between Vs and Vnc. Remember, Nc was the in phase component of the noise. This again is a time dependent variation that you might add. So I'm looking at an instantaneous picture of the phasor diagram. And then you need to add the quadrature noise. Remember, that was minus I times the VNS, hence this particular direction. You can easily make out that to this vector, essentially I'm adding something which is multiplied by the minus of the complex number I, right? Uh, so I have to essentially multiply by exponential minus I pi by 2 for me to get this VNS. So that the addition of these three quantities actually gives rise to this green curve, right, which is my V of t. This is the detector, the voltage at the detector as measured, which includes the signal and the two components of the noise, which is the in phase noise and the quadrature noise. Now remember that in my phasor diagram, this Vs of t is actually going around, in this plane at a frequency omega. So omega times t forms the instantaneous angle which it makes with respect to the the x-axis here, which is the real part, right? So this is how actually all of these are essentially rotating about this, and my instantaneous real part of the signal that is detected at the detector is simply a horizontal projection of this final green vector at any instant in time, right? So that is what is detected. So this horizontal length from here to here, which is the projection, is precisely what is instantaneously detected at the detector, right? So this kind of represents for us, this is the mental view you should have of these two quantities. Remember that because these noise parts are varying randomly and they average out to zero, these actually form a sort of a circle around the Vs, and they can take any value within that circle, with some certain quantity. So these are not really fixed in time, but these are varying in time such a way that their averages are indeed zero. So let's look at the nature of the noise. So let us consider the properties of the noise. So essentially I am looking at the two quantities, which is VNC and VNS, right, which are the in phase and the quadrature noise. And to characterize the noise, one looks at basically a distribution. So the probability distribution function for the noise is given by this PVNC. So PVNC simply tells me what is the probability of finding a particular value VNCT at a time t, for example, a particular value between the limits VNC and VNC plus DVNC, right? So this is a range of values that VNC can take. And one is asking what is the probability of finding VNC in a particular imagine that there are multiple baskets, and each basket has a width of dVNC, and one is asking in which basket precisely what's the probability of finding a particular VNC in a particular basket. That is precisely what the probability distribution function gives like. And clearly you see that it is a Gaussian distribution, right? Um, you have the exponential minus VNC square by 2 sigma square. Sigma clearly is the standard deviation. This is a very standard representation of the Gaussian noise, right? So what it is telling you that the most probable value of VNC is actually zero. Okay, uh, and very small values is where it peaks. VNC can take positive and negative values centered at this VNC equal to zero, and there is a this is the probability distribution normalized such a way that when I integrate this VNC from minus infinity to plus infinity, I would get a value 1, right? That is what gives makes this PVNC DVNC as a probability distribution function. Absolutely similarly, just like we had for B and C, we also have a similar yet independent distribution of VNS. That is the in-phase noise and the quadrature noise. Both are Gaussian. Both are such that they are a Gaussian distribution about zero being their central value, which is the peak value, and the distributions kind of fall off on either side in the exponential way. So now let us look at a few relationships of this Gaussian function. Remember in the early half of the course, we had looked at how to integrate Gaussian functions, and this is precisely what I have used here. So you can see that you can integrate from minus infinity to infinity, P, V, and C, D, V, and C, and this is actually equal to 1. So this is a normalized Gaussian function, and you can clearly see why we put this prefactor of 1 over square root 2 pi times sigma, that is to ensure that this is normalized. Now clearly PVNC is a probability distribution function. Now so please understand what probability distribution means. So I have got noise and I'm keeping record of all these values of VNC in time. And what I do is basically from my record, now I can look at what is the chance that I got a particular value of VNC. That is, imagine I have 100 measurements, and you see that let's say 10 or 15 measurements are when VNC is 0. There are a few measurements with a particular value of VNC and so on. So if you plot this distribution of the probability, what is the the uh, total probability of finding a particular value of VNC, you will see that that's a Gaussian distribution. That is precisely what I mean uh, by a Gaussian noise. Now, so again, when I'm looking at, for example, average of a certain quantity, for example, I'm looking at the average of VNC, right? You see that all that I need to do is uh, put in VNC, the object that you want to average, and then multiply it by the probability distribution. So what this is doing is basically a weighted average. If you do this weighted average, you will see that the average of VNC, as I mentioned, is actually 0. It is centered and maximum at VNC equal to 0. So that is the average value, and it is symmetrically distributed about this average of VNC equal to 0. Now one might ask, okay, what about the average of the square? Certainly, you will see that the average of the square of these VNC which are fluctuating in time cannot be sitting at 0. So VNC square average, so you can actually do this, right? And the way to go about doing it is essentially, take the derivative of the argument of the exponent, and you will see that having such a derivative, you'll be able to easily calculate this. I urge you to do that. So that's a trick there. So by looking at the earlier relationships, one can actually do this, right? From this first equation to this, and you will see that this comes out to be simply sigma square. Whereas you can go ahead and again now take the second derivative of the argument of the exponential, and rearrange the terms, and that's a way to again do it. You can look at now uh, the next fourth power of VNC, right? And you see that this is precisely what one is calculating. And now the fourth power of VNC, when averaged over the Gaussian distribution, actually gives me 3 times sigma to the power of 4, right? So these are some relationships and some averages that we will use, but you should be able to do these. Let me just mention that this is what is called, as the first moment of that the random variable. This is like, the second moment. Then you have the third moment that we are not calculated or shown here, but the fourth moment is this. And you will see that all the odd moments, that is VNC average, VNC cube average, VNC to the power of 5 average, all of these will actually turn out to be 0, right? So that is precisely what a Gaussian distribution does to your uh, uh, to the averages that you're looking at. So now we are going to deal with a very important idea of that of ergodicity and time invariant phenomena. These ideas come from statistical physics. So the whole point is that I have got a random variable A. I want to look at its average, and I have got a probability distribution function that governs the occurrence of A, that is P of A dA. So there are two ways of doing the average. One is that you create identical copies of the system and then look at the occurrence of A in each of those copies. You have created an infinite variety of them. This is what we say as a creation of an ensemble, and then average over all such possibilities. The other averaging method is to simply let the system evolve in time, and A being a random variable is going to take all kinds of values within that time. If you wait sufficiently long enough, then the system is known that the random variable is supposed to take on all possible values that it ever can. And in the limit that t tends to infinity, the averaging which I am showing here On the right, this is 1 over t minus t by 2 to plus t by 2 a of t dt, looking at all occurrences of a within this time capital T, and in the limit that t tends to infinity, this is the quantity that I calculate and call this as the time average. And what I described earlier with creation of ensembles is this left-hand side quantity, which is the ensemble average. And the statement is that for time invariant phenomena, the averaging over the ensemble is equal to the averaging over time in the limit that t tends to infinity. So this ensemble average being equal to time average is a fundamental idea of statistical physics, telling you that for time invariant phenomena and for ergodic phenomena, that would mean that A takes all possible values that it can if you wait long enough, and these two averages are the same, right? Um, in the context of our treatment, we are looking at power as the measurement. Remember, we are looking at square law detectors. That would mean that I don't measure V, but I measure uh, the product of the V, right? So the average can be written down as half of V of t exponential I omega t times this complex conjugate, which is V star exponential minus I omega t. So half is simply coming from the terms that arise into this. So I would request you to just take the real signal, right, and look at the instantaneous power, and you look at this quantity which I have just mentioned here, and you will see that indeed these two quantities are true. These two quantities are equal, and hence this definition of P of t is indeed true. Now, when you look at V of t itself, you see that there is going to be quantities coming from the signal, that is Vs, from the uh, in phase noise, that is VNC, and the quadrature noise VNS. So this is going to be V of t is particularly going to be Vs plus VNC minus I times VNS, right? And multiply this with this complex conjugate, which is Vs plus VNC plus I times VNS. You will see that essentially you will get 9 terms. And you see, if you collect all these terms, the terms that contain V and S comes with a plus minus I, and they get cancelled out. So eventually you are left with these 4 terms, which is the instantaneous power at a time t, which is simply Vs square at a time t, Vnc square at the time t, Vns square at the time t, and Vs times Vnc at the time t. Remember, I have not averaged anything here yet. I'm just looking at the instantaneous power. So if you look at now the average power, right, it will be simply the average over what I had written down earlier. So you see that because the cross term uh, had it contained Vs times Vnc, which is the first moment in a sense, that is right. It is we need to average over the probability distribution, which is the Gaussian. You see that that first moment will give me 0. So that term really doesn't contribute, and you have only the square terms contributing to the average power. So my average power turns out to be, you know that the second moment of VNC square and VNS square is both going to give me sigma squares, and hence this is twice sigma square here, and this is the average power that I have. On the same vein, I can now talk about what is the fluctuation or the root mean square fluctuation in this power which is coming at the detector. Now remember, the fluctuation is arising because of these two noise terms, right? So I need to do the following. To calculate the root mean square, first I take the instantaneous power, subtract from it the average power, then square that quantity, and then average and then take the square root. So that is what eventually this comes out to be. If you look at all the cross terms and so on, you collect them, you will see basically you find the following. That is, you take the square of the instantaneous power and then average it and subtract it from the average, which is squared. Please remember the sequence in which you do. First you square and then you average. In here, you average and then you square. Once you take the difference, you take the square root, and that is your RMS power fluctuation. And this you can calculate. We know that the average power itself simply goes like Vs square average times half. This is by definition of power, and you know the complex conjugation definition that we put in. That so this is the power in the signal itself. So that comes in here, and then you sigma square you get from uh, these averages that are coming out from both VNC square and VNS square and times sigma. So this is, I urge you to do the calculation and convince yourself that this is indeed the result of this calculation when you put this above formulation here, and this is what you would get, right? Uh, Now let us look at it a little pictorially, and that is what I will show you in the next slide. Right. So uh, pictorially, one can think of it like this, that this my power is varying in time, right? That's my instantaneous power. On my x-axis, I'm plotting time. And one can think of an average power, which is the averaged quantity taken over this variation, and it's averaged over this Gaussian distribution of noise, right? And you would get the average P. I have represented that by a level which is black. And you see that RMS variation is basically going to give me some measure of the fluctuation within which this, this whole signal lies, right? So the total power at the detector basically dominantly lies between at the average and within 2 times delta p, which is twice the RMS power fluctuation, right? So that is the kind of mental picture that one must have of this power. So let us assume now this is the important result that I'm going to come to. What I'm asking is, what is the limit, the minimum power which is detectable by me, right? So I have got a signal that is submerged in noise, and the claim I am making is the following, that the limit of my detection is that if my signal is equal to the RMS power fluctuation, then that is the limit of detectivity for me. Anything below that will be lost in noise. Anything just above that was definitely signal. So you see that it gives me a nice measure. The limit of detectivity happens to be the RMS power fluctuation. So that is what I am claiming as the limit which I can detect. So if I just put in this fact, that is my PS, I'm calling as my P limit. This is my level of the signal itself, right? The minimum signal which I can detect. And similarly, this is equal, this my delta P is equal to P limit. And I can rearrange this, and you can clearly rearrange, and you will get a quadratic equation whose the solution in which you add up noise is the one you will pick up. You see that P limit, the minimum limit of the power which I can detect is basically depends on the sigma square, you know, and it is 1 plus square root 2. This is a factor that comes out naturally if I claim that my signal is such that the minimum signal one can detect is equal to the RMS fluctuation itself. So what it is, basically, telling me that the limit of detection is basically noise times 1 plus square root 2. So that is my power level associated with my signal. If it is larger by a factor of square root 2, right, in terms of additively, it's larger by a factor of square root 2, then you see that I would call that as my minimum level of detectivity, or the limit of my detection, right? Here again, I have used these facts, which are my the second derivatives, uh, the second moments of my the in phase noise and the out of phase noise, or the quadrature noise. The second moments all give me sigma square, right? And then P noise by definition would be half of this 2 sigma square, which eventually comes out to be sigma square. So that is precisely what I have used here to get to this very important result on what exactly I call as my limit of detection given a certain amount of power in the noise. So until now, we have looked at quantities which are largely in the time domain, or we have also looked at ensemble average. But now we want to look at these same quantities, that my signal v of t, in the Fourier domain. And you know the importance of Fourier. Apart from that, you will see that lots of these very interesting results on noise and analysis of noise turn out to be quite elegant in the Fourier domain. And that is why something that we will go back and forth between the Fourier and the time domain. So to begin with, let me give you some definitions. Right. So here I have the definition for a Fourier transform. Let's say v of t is my signal. I multiplied by this kernel for the Fourier, which is exponential minus I omega t, integrate over time from minus infinity to plus infinity, multiply by 1 over 2 pi to get my signal in frequency space. This is my Fourier transform definition. Absolutely similarly, right? Absolutely similarly, I can look at the inverse Fourier transform, right? Here you have the uh, Fourier transformed signal in frequency put back here. Now we are multiplying by exponential plus I omega t. Note the difference in sign. And now I'm integrating over all frequencies, right? From minus infinity to plus infinity, and I get back my signal v of t. Remember, going back and forth, I need to multiply this 1 by 2 pi factor. That is because I am integrating in time here with omega. So I need to, multiply this 1 over 2 pi factor. But you see that this has to be done as you go back and forth. You could have either shared it with the inverse transform, you could have shared it between the two and so on, but we will follow this as our definition of the Fourier transform. So please keep this in mind. We'll be using it a few times uh, through this. Now there is a catch. The catch is the following, that when I'm looking at a Fourier transform like V of omega, there is a problem that when I'm looking at this Fourier transform, I am never integrating in reality from minus infinity to plus infinity. I'm always integrating from minus t by 2 to plus t by 2. That is my reasonable time within which I integrate. It is always finite. And usually when it talk about detection, this time t, capital T, is related to the resolution, in a sense, of the time I require to keep my detector on to detect the signal. So that is precisely the time t that comes uh, into the averaging process, or other integration process. So here I'm looking at the Fourier transform. So what I'm going to do is, because I'm going to look at this sort of a transform which it doesn't integrate from minus infinity to infinity, plus integrates only till the time t, I'm calling that as Vt omega. This is a Fourier transform of V of t with in a finite duration time, capital T, is where the integration has happened. That is what this V subscript T omega refers to. And when I'm looking at the inverse transform, of course, I do the same, which is I integrate over all frequencies, right, from minus infinity to plus infinity. And there is no issues. I always make sure that I integrate from minus infinity to plus infinity in frequency, and I get back my V of t. Now remember that V of t is the same signal that we have talked about earlier, but just that when I'm uh, in practice, when I'm integrating, my resolution time, the finite resolution time of the system, governs the time duration over which I integrate. And that is different. Vt omega is different from V of omega, which is the ideal Fourier transform that I have. Right. So again, I know that my signal is real, so there are consequences to it. What does it mean? When I'm saying that my signal is real, it means that if I take its complex conjugate, then because the signal is real, these two quantities are equal. And because we have chosen the signal to be real, there is a consequence. The, the Fourier transformed signal, that is Vt omega, is actually becomes equal to the complex conjugate of it, Vt star omega, but not omega really, if I substitute my omega to the negative frequency components. Remember again that the integration over negative frequency is a mathematical step, and what it is telling me here is that the negative frequency content, okay, and if you complex conjugate it, it's precisely the content in the positive frequency part. That is precisely what this statement is telling you, and because signal is real, this relationship is true. And let me just go ahead and derive it for you carefully. Right, so let us look at our original definition of the inverse transform. My Vt omega was the time averaged, or rather the finite time Fourier transform. Let me use that word now to represent that. So Vt omega, when you take the inverse Fourier transform, you integrate from minus infinity to plus infinity Vt, and you get back your signal in time. Now, if I take the complex conjugate of that, this particular expression, on the right hand side, I need to take the complex conjugate of every complex quantity here. That is, my Vt omega becomes Vt star omega. My exponential I omega t, its complex conjugate is exponential minus I omega t and d omega. Now you see that you just make this transformation of the dummy variable omega going to minus omega. You see you will get the following relationship. That is, you need to change now the uh, the limits of integration, because omega goes to minus omega, plus infinity goes to minus infinity. So my limits of integration goes now from plus infinity to minus infinity. My Vt omega star is going to Vt star again, but minus omega. And exponential minus I omega t has become exponential plus I omega t. And uh, my integration time scale, or rather frequency uh, bin, is becoming d of minus omega. So now if you rearrange, because of this minus omega, I can realign my limits of integration. So I get back my minus infinity to plus infinity again, because I lost this minus omega, and you get this. Now if you compare this particular expression with my original definition, we clearly see that uh, that because v of t is equal to v star of t, it implies that Vt omega, that is the finite time integrated Fourier transform, is equal to Vt star minus omega, right? So this is a very important result arising out of the real signal. Now, if you look at, you can do it another way, which is to simply, take the definition of Vt omega, uh, look at the quantity Vt star. So you take the star of everything, and you take also the parallelly you would make the transformation of omega going to minus omega, and you see that you will get the following form. I have taken Vt and taken the star of it. Here I have taken the star, but I have taken omega to minus omega, and you rearrange all this, what you get is precisely this form, right? So because my Vt star is same as Vt, I get back this exponential minus I times minus omega, and then the complex conjugate, I get back to minus I omega t, which precisely is the definition for Vt omega. So there are multiple ways of looking at the same thing, but you see you can arrive at the same result. So now let us look at another important aspect, which is to look at the signal in the frequency space. So we're going to talk about something called the spectral density function. We will derive it, and particularly it will tell us what is the amount of uh, energy distribution in the signal, which is contained in various bins of frequencies. So let us look at it mathematically. So here I have the instantaneous power, which is v square of t, and what I'm interested is in looking at the average power. And you know that one is doing a time average here. So this is by definition simply 1 over t. You integrate from minus t by 2 to plus t by 2. This is v square dt. Now you see this v square, I can split this as as v of t times v of t, and for one of them I go into the uh, frequency space, right? So I'm looking at the Fourier transform of one of the v of t's, right? This is actually the inverse Fourier transform. Remember, from we are going from the omega space back to t space. So I can write down my v of t as minus infinity to plus infinity vt omega exponential I omega t d omega, right? Now we do know that the signal that we are talking about is real, right? Our v of t is indeed real. That would imply that my vt omega is same as vt star minus omega, right? So you can see the direction in which I am going. So this is our previous step. I had looking at the integrated power, and then I'm averaging it. So this was my vt star minus omega because my v of t was a real signal, right? Um, Now you see, because I've got minus omega here sitting in my argument, I can go make a transformation from minus omega to plus omega, right? So that is just a dummy variable of integration. So you see that my d of minus omega will give me a minus sign. I would have interchanged my limits here, exactly the same thing that had happened here. And my omega here has gone to minus omega, and this is the new expression that I get. Now, what I do is I take this minus sign and now interchange again from minus infinity to plus infinity, and my integration constant has come here. Now what I'm doing is I am changing the sequence in which I'm going to integrate. So you see here that my capital T, V T star omega, I'm going to first integrate that, uh, integrate the time now, and then look at the integration in frequency later. So the only time dependent function is this v of t that remained as it is. There is a dt that is coming in. And of course, there is this uh, kernel or Jacobian exponential minus I omega t, which is coming from the Fourier transform, right? So I put that together. So imagine minus t by 2 to plus t by 2 vt exponential minus I omega t dt, you will clearly see that this is indeed the definition of the finite time Fourier transform, right? Of course, they are multiplied by 2 pi because 1 over 2 pi times this was the definition of Vt omega. So you see what I have gotten here is now Vt star omega, Vt omega d omega, and I now need to integrate from minus infinity to plus infinity. So you see this change of the uh, order of integration or interchanging them is a crucial step here. Of course, invoking also the fact that my signal is real. So now that we have got, this is essentially what is my power, right? Time integrated power. That's what this is. So let's see what that means. I'm rewriting it as the mod of Vt omega square integrated over now frequency. Okay. Now you see, remember that the frequency content in the negative frequency space was related to the positive frequency space, right? And there was nothing new in it. So I can, rather than, because I'm looking at a mod square of that function, I can as well integrate from 0 to infinity, and I multiply this whole factor by 2 because everything that is there in the negative frequency space is precisely what is there in the positive frequency space. So this would be my result, important result, that my average power, which I had integrated in time, is now equivalently sort of the average power with an appropriate factor 4 pi by t integrated over the finite time averaged spectral uh, function, right? So this particular object, within the integration is what I call as a spectral density function, right? which is simply 4 pi by t Vt omega mod square as my spectral density function. Now remember, I will call it spectral density function only in the limit that t tends to infinity. That is, I need to make sure that my signal is more or less, this business of ergodicity and stationarity and all that one is putting it all together. And we will see that this SV of omega becomes a unique quantity only if you allow this t tending to infinity limit of this spectral density function, right? So this is our definition of the spectral density function, and let us see how it looks like pictorially. So you should think of it like this, that my V of t is my input signal, right? I can put this input signal through various bandpass filters, which are sort of breaking up into various bins. This is the first bin is centered at omega 1 and has got the width of delta omega, right? Second bin at omega 2, So you see that the whole spectrum is divided into now bins, and as the V of t comes in, different spectral bins will contain different amount of energy. So that is precisely what one is measuring. One is measuring the power content at omega 1 in the bin delta omega about that frequency omega 1. So you see, you'll get a number here. So this is precisely, the collection of all these from omega 1 to omega n is precisely the spectral density function that I am talking about. So the way to interpret it is that my SV omega d omega is basically the amount of power in the signal within the limit omega plus omega 2 omega plus delta omega. So within that limit, you have the following interpretation of the spectral density function. I am rewriting it just to emphasize it again. The spectral density function SV omega d omega can be thought of as average power of the signal, okay, the signal being B of t, with the frequency components that lie between omega and omega plus d omega. So this is our definition of the spectral density function, and this we are going to use multiple times, and this is going to be important that moment we have a signal in time, one can as well look at its finite frequency representation through the Fourier transform. Take the mod square of that, multiply by 4 pi by t, and integrate, take the limit of t tends to infinity that is large enough time for constructing that Vt omega, and then you would get the spectral density function, which is a unique representation of V of t in the spectral domain.